Hey everyone, and welcome to The Explainer. So today, we're popping the hood on something you probably use all the time, but maybe haven't thought too deeply about: Docker images. We pull them, we push them, but today we're going to see how they actually work. We're going from just running containers to becoming master builders.
All right, I want to start us off with what sounds like a pretty simple question. What exactly is a Docker container image, right? We talk about them literally all the time, but physically, tangibly on your hard drive, what is it you're actually downloading? I want to challenge your basic assumptions here, because an image isn't just some magic black box, and it's definitely not a monolithic block of software.
So, here's our game plan for today's explainer. First, we'll look at the anatomy of an image. Then, interactive image creation, building with Dockerfiles, multi-stage builds, and finally, we'll wrap up with some essential Dockerfile best practices.
All right, section 1, anatomy of an image. Let's get into the layered file system.
Okay, so you might know the golden rule of Linux. Absolutely everything is a file. The whole operating system is basically just one big file system. Well, a Docker image, it's fundamentally a giant tarball made up of multiple, unchangeable, or immutable read-only layers. Docker uses a clever little thing called a storage driver to seamlessly merge all these stacked layers together. So to the container running inside, it just looks like one single perfectly unified virtual file system.
Okay, let's dive into this stack and see how it builds. Every single Docker image starts at the very bottom with what we call a base layer. Now, this base layer is usually an official image straight from Docker Hub. Think of a lightweight Linux distro like Alpine or maybe Ubuntu. From there, every new layer that gets stacked on top, it only contains the delta, meaning it just holds the specific changes made relative to the layer right below it.
Let's move to a practical example to really see how this works. Imagine we're making a custom image for a web app. Our base layer down at the bottom is Alpine Linux. Boom. The next layer up, that's just us adding the Nginx web server. And finally, that third layer on the very top contains our specific web app files, the HTML, the CSS, the whole shebang. And here's the absolute crucial takeaway. The second these layers are generated, they are locked tight, completely immutable. They can never, ever be changed.
Now, you might be wondering, if all these image layers are totally read-only, how does a running container actually do anything? Well, when you fire up a container, Docker just takes that locked stack and slaps an incredibly thin writable layer right on top of it. This is exactly why containers start up so unbelievably fast. There's no booting a whole OS. Docker just relies on those cached layers and gives the active container a tiny little scratchpad on top to work with.
But wait, what if the container needs to tweak a file that's buried down in one of those locked read-only layers? This is where the magic really happens. Docker uses this super efficient file sharing trick called copy on write. It is literally the secret sauce for why Docker is so storage efficient. If a layer just needs to read a file, it looks right through to the layers below. But if it needs to modify it, it does something incredibly clever.
Let's think about a specific file. Let's call it file 2, sitting down in the base layer. Let's say the writable layer above it wants to modify that specific file. Well, before it can do that, the copy on write strategy kicks in. It physically pulls a copy of file 2 up into its own layer, and then it makes the modification. This leaves the original file down in the base layer completely untouched. It only pulls the file up at the exact split second a modification occurs. Pretty brilliant, right?
Moving right along to section 2, interactive image creation. We're going to look at the manual approach.
So if you want to build an image the old school beginner way, there are 3 manual steps. First, you run a base container with an interactive terminal. Second, you manually type out the commands to modify the file system inside that running container. And third, you exit out and commit those changes to save them as a brand new image. Now, I'll be honest with you, there is a lot of friction here. It's kind of tedious, but let's see what it looks like in action.
All right, imagine a real terminal session. We've interactively launched an Alpine container. Out of the box, Alpine doesn't have the curl utility installed, so we gotta manually type out the update and install commands. Then you just sit there and watch the package manager reach out, grab the files, and install them directly into our container's top writable layer.
Now, once we exit that container, it just sits there on our system with an exited status, waiting. All those curl files we just installed, they're trapped in its writable layer. To save them, we can use the Docker container commit command to permanently bake those changes into a new image. But guys, a quick warning.
This human-driven, step-by-step process, it is heavily error-prone. It totally relies on you perfectly remembering every single command you typed. For real-world infrastructure, it is definitely not scalable.
Which brings us nicely to Section 3, Building with Dockerfiles. This is all about declarative automation.
This represents a massive shift in how we approach this stuff. We're moving away from the imperative way, manually giving step-by-step instructions like we just did, and moving toward a declarative approach. A Docker file is essentially just a text document where you describe the automated expected outcome. You just tell Docker, hey, this is what I want the final image to look like, and the builder handles all the heavy lifting to construct it. To draft this master blueprint, you really only need a handful of essential building blocks. From defines your starting base image. Run executes a Linux command, like installing tools. Copy grabs files from your local computer and drops them into the image. Work direct sets your default folder context. And finally, CMD tells the container what default process to run when it wakes up. Simple as that.
Now, what's really interesting here is the aha moment it gives us. Notice how the instructions in a Docker file map directly to the physical image itself. Almost every single line of code in that file creates a totally distinct physical read-only layer in the final output. That from command at the top, that is your base layer. Your first run command, boom, that creates the next layer. Your code literally transforms into the physical architecture.
Okay, let's shift gears to the climax of this explainer, Section 4, Multi-Stage Builds. This is how we get hyper-efficient images.
260 megabytes. That is the shockingly massive size of a basic, completely unoptimized Hello World app written in C. I mean, why on earth is it so huge? Well, because when it was built, the creator accidentally packaged the entire Alpine software development kit inside the final image. We're talking compilers, linkers, the works. And here's the thing. You absolutely do not need a compiler to run an app in production. You only need the finished binary. Now contrast that with this tiny number, 136 kilobytes. This is the exact same fully functional C application, but it was built using a multi-stage build. We just reduced the image size by more than 3 orders of magnitude. No way, right? It's incredible. So the crucial point is how we actually pull this off. In your Docker file, you set up a first stage dedicated purely to building. You install the heavy SDK, compile your code, and get your binary. But then you define a second, completely fresh, empty stage, usually using a blank image called Scratch. Then you use the magic command, copy-from build. You selectively pluck only the compiled binary from stage 1 and drop it into stage 2. That entire bloated SDK, just left behind and discarded. It's a total game changer.
All right, bringing it home with Section 5, Dockerfile Best Practices. Let's look at the golden rules for master builders. Here are your key takeaways to wrap this up. First, treat containers as ephemeral, meaning they should be totally disposable and replaceable in seconds. Second, try to combine your run commands to minimize the total number of layers. This keeps your file system fast. Third, order your commands smartly. Put the code that changes all the time at the very bottom to leverage Docker's layer caching and massively speed up rebuilds. And lastly, always use a .dockerignore file. It keeps your build context lean and significantly reduces your security attack surface. To wrap up our explainer today, I want to leave you with this final provocative thought. Take a hard look at your existing legacy applications. The ones chugging along on clunky VMs or bloated servers. How much leaner, faster, and more secure could they be if you containerize them using these multi-stage master builder techniques? The tools are declarative, they are insanely efficient, and the power is literally at your fingertips. So get out there and start optimizing your infrastructure today. Thanks for hanging out with me on The Explainer.